Let's go. So I promised you yesterday to give you the algorithm that allows to compute homology. Let me just recap what we've seen. Yesterday, I defined simplicial homology. And in order to do so, we had to introduce a few notions. We talk about chain complexes. That is the sequence of vector spaces that are the n chains connected by boundary maps, boundary operators. And thanks to these boundary operators, we defined the n cycles, the n boundaries, and the nth homology group, being the quotient, the vector space quotient of the cycles modulo the boundaries. And today, we're gonna see how we can compute them in practice with the computer. And thanks to the algorithm we will describe, we will be able to understand a little bit more how this works. And so we will understand better what does homology group means. So I will start with the standard algorithm for computing homology. It is called the incremental algorithm. Then I will show you some application, and we will finish the lesson by a matrix version of the algorithm, which is the one used in practice. So the algorithm we will describe is called incremental because we will study the homology of our simplicial complex step by step by adding simplices one by one. So let K be a simplicial complex with n simplices. I will first order my simplices. So I will say which one is the first simplex, which one is the second simplex, and so on. And what I ask for this ordering is that if you have a face of a simplex, then this face should appear before the simplex itself. So it is an increasing sequence of simplices. Okay, there are many ways of ordering such simplices. And I give an example here. Say that my simplicial complex is this one. So the ordering is, so we will look at our simplicial complex simplex by simplex. I have the input simplicial complex, K, and I will order the simplices. That is, I will pick an order of the simplices. I have to say which one is the first simplex, which one is the second simplex, and so on. And my ordering has to satisfy one axiom. I want that the face of any simplex appears before the simplex itself. So for instance, if I have an edge and the vertex of its edge, I want the vertex to appear before the edge. Tiago asks, is it easy to show that this total order always exists? This is really easy to show because you can just say you first add all the zero simplices. There is no problem. Then you add all the one simplices, then all the second simplices in the order you want. Yeah, you increase dimensions one by one, and this is a total order. We will see with persistent homology next week that the ordering of the simplices is important. But for today, choose any ordering. And so, yeah, this was the example I gave. I just add every vertices one by one, and then the edges, and then the unique triangle. And we're done. Lucas asks, but the zero-dimension simplices don't have an order among them. Now, when you have a simplicial complex, there is no order on zero simplices or any simplices. But what I say is that you can choose any order of the zero simplices. You can add them in any order you want. This will be an order which satisfies this axiom. So choose any order of the zero simplices and add them. Then choose any order on the one simplices, then add them. Any order on the two simplices, add them. This is an ordering that will satisfy this axiom. And now I will consider simplicial subcomplexes of my complex K. I define K to the I to be the set of the first I simplices. And fortunately, thanks to this axiom here, this set, Ka, is a simplicial complex. It is a subset of K that is a simplicial complex. You can check the definition of a simplicial complex. You just have to make sure that every face of a simplex is also a simplex, is included in the simplicial complex. And this is true because of this property. And remark that going from Ka to Ka plus 1 consists in just adding one simplex. So we have this sequence of simplicial complexes, where the first one consists of simply one vertex, and the last one is my whole simplicial complex K. And the incremental algorithm we will use consists in finding the homology of each of these simplicial complexes. And to do so, we need a notion that is called positivity. So consider a sequence, an ordering of my simplices, and consider the corresponding sequence of simplicial complexes. Pick any integer, I. Consider the ith simplicial complex in my sequence. So we add one simplex. I say that this simplex is positive if there exists a cycle of the ith simplicial complex that contains my simplex. If it is not positive, we say it is negative. Excuse me. Having a cycle that contains my simplex means that I can find a cycle. So a cycle is a sum, a formal sum of simplices. If there exists a formal sum of simplicial complexes that contains my simplex sigma I, and being a cycle meaning that its boundary is 0, then it is positive. So for instance, every vertex is positive because the boundary of a vertex is 0 by definition. If I take the cycle C equals to sigma 1, the first vertex, it is a cycle that contains my simplex, so I say that it is positive. The second vertex, sigma 2, also is positive because it has boundary 0. Sigma 6, oh no, sigma 5, sorry. I'm looking at this edge, the first edge that enters the simplicial complex. It is negative because you cannot find any one cycle that contains this edge. How can you see that? In this simplicial complex K5, you have only you have two one chains. You have the chain 0 and the chain sigma 5. But the chain 0 does not contain sigma 5. And the chain sigma 5 is not a cycle, because sigma 5, its boundary is the sum of its vertices, and this is not 0. Oh, let me just correct the drawing. This should be sigma 5. And here I forgot to draw the vertex. All right. Sigma 8, this is a positive simplex. Indeed, I can find a cycle that contains sigma 8, and the cycle is this one, C equals to the sum of the 4 edges. And as we've seen yesterday, when you compute the boundary of such a sum, you have vertices that cancel. The boundary of C will be the sum of the vertices of the first edge plus of the second edge plus the vertices of the third edge and the vertices of the last edge, right? And you obtain the sum of all the vertices counted twice. And as we work in Z over 2Z, 1 plus 1 is 0. So this sum is 0. Okay. Included in a chain, Lucas asks, means that I can find a chain. So a chain is a formal sum of simplices, where basically a chain can be written as the sum over all the simplices of dimension you've chosen times 0 or 1. If I have a 1 before a simplex, I say that it is included in my chain. So what is it useful for? First, a remark. When I add a simplex in a simplicial complex, the only groups between the cycles and the boundaries that may change are the group of cycles of dimension D, where D is a dimension of my simplex, or the group of boundaries of dimension D minus 1. When you add a simplex, you cannot change homology everywhere in your simplicial complex. You can just change the cycles of the same dimension or the boundaries of the lower dimension. Okay? And now a lemma. If my simplex is positive, then what happens when I add it to the simplicial complex? I increase the Betti number of my simplicial complex, the Betti number of dimension D, by 1. Okay? And all the other Betti numbers remains the same. So adding a positive simplex to my simplicial complex creates a homology class, creates a homological feature of the dimension of my simplex. So let's prove that. Say that my simplex sigma I is positive. I can find a cycle that contains it by definition. And I will prove that this chain C is not homologous to a cycle in Ki minus 1 That is, this chain is not homologous to a cycle that does not contain sigma I. So this is very easy. By contradiction, I suppose that I can write my chain, my cycle C, as the sum of another cycle and a boundary. Because being homologous, let me recall you that it means that you are equal up to a boundary. Then if I take the difference in this equality, I obtain C minus C prime equals to a boundary. But remark that in C minus C prime, sigma I is included in this chain, C minus C prime, because C contains sigma I and C prime does not contain sigma I, because C prime is a chain of Ki minus 1. And we just added sigma I. So we have a boundary that contains the simplex sigma I, and this is absurd because we just added sigma I. So it cannot be in the boundaries, it cannot be the face of a simplex. Because if it is a face of a simplex, this simplex will be a dimension higher, and the ordering we chose on our simplicial complex is such that faces arrive before the simplices. All right, so sigma I is in a cycle that were not present before. This means that the vector spaces of cycles is increased by 1. The dimension is increased by 1 because we have a new class. Okay, so we now I will prove that the dimension of the boundaries remains the same. And to prove so, what do I do here? I take a cycle that contains sigma I, and I want to what do I do? I prove, all right. I take a cycle that contains sigma I, and then I prove here by computing boundaries that my cycle plus sigma I is okay, sorry. The boundary of sigma I is equal to the boundary of C plus sigma I. Moreover, C plus sigma I is a chain of K I minus 1. This is because C plus sigma 1 is not, it does not contain sigma I. So the simplex I added, sigma I, does not create new boundaries in of dimension d minus 1. So the boundaries of dimension d minus 1 remains of the same dimension. Okay. Yeah. So then I can conclude about the Betti numbers, because remember that the Betti number is the dimension of the homology group. And we prove that it is equal to the dimension of the cycles minus the dimension of the boundaries. The dimension of the cycles is increased by 1 in dimension D, and the boundaries of dimension D remains the same. So at the end, the dimension of the homology group is increased by 1. And if you look at other dimensions, all the groups remain the same. So the Betti numbers remains also the same. I hope it was clear enough for you. Please interrupt me if you have any doubts. Okay, this was what happens for a positive simplex. Now let's look at negative simplex. When I add a negative simplex in my simplicial complex, then the Betti number of dimension d minus 1 dimension lower, is decreased by 1. And all the other Betti numbers remain the same. In other words, when I add a negative simplex in my simplicial complex, I destroy a homology class of dimension 1 lower. Okay. A proof. Same, we start by proving intermediate fact. If my simplex is negative, then its boundary is not a boundary of k to the I minus 1. I consider its boundary, so sigma I is of dimension d, its boundary is of dimension d minus 1, and I will prove that this is a new boundary in k I minus 1. To prove so, by contradiction, I suppose that I can write the boundary of my simplex as the boundary of a chain of k I minus 1. I obtain that the boundary, so the boundary is linear, so I can do the difference here. I obtain that the boundary of sigma I plus my chain is 0. But remark that C plus sigma I is a chain that contains sigma I, because sigma I is not in C. So when I take the sum, we have a chain that contains sigma I. I have a chain that contains sigma I, and this chain is a boundary, is a cycle, because its boundary is 0. But by definition, this means that sigma I is positive. This is a contradiction, because I suppose that it is negative. Okay, so I prove that its boundary is new in k I minus 1. So the boundaries of dimension d minus 1 have a new class, meaning that the dimension is increased by 1. All right. The dimension of the cycles of dimension, I should say d minus 1 here, remains the same. So we can use the relation between dimensions to see that the Betti numbers of dimension d minus 1 is decreased by 1. Let me correct something. Yeah, this should be here d minus 1, d minus 1, and here we use a relation at d minus 1, 2. So I just prove here that the Betti number in dimension d minus 1 is decreased by 1, and you can prove the same way that the other Betti numbers remain the same.
Professor?
Yeah.
What's the reason that the boundary has the dimension increased by 1? Use it what we proved.
Yes, I did, because I proved that the first sentence is the boundary of sigma I is not a boundary of, is not an element of the boundaries of k I minus 1.
Okay, if you add another point to a space vector, you have another dimension, right?
Yeah, this is what I mean. Yeah.
Okay,
Exactly.
thank you.
Yeah, you can see the boundaries of ki minus 1 as a subset of the boundaries, as a linear subspace of the boundaries of chi a. And so in chi a, we have an element that was not here before. So yeah, you add an element, you add a dimension. That's it.
Okay, thank you.
Please. Okay. So we've seen that adding a positive simplex increases the dimension of the Betti number of dimension d, and adding a negative simplex decreases the dimension, the Betti number in dimension d minus 1. So now we can easily compute the Betti numbers of our simplex k by simply following this algorithm. So we add the simplices one by one. This is here for I from 1 to n. Let d be the dimension of the new simplex. We add. If it is positive, then I increase. Oh, a mistake again, sorry. If it is positive, beta d is increased. And if it is negative, beta d minus 1 is decreased. I'm just following these two lemmas here. I put the condition if d is greater than 0, but this is, you don't need actually this condition because each simplex of dimension d is positive. Okay. So let me show you an example. This is the simplicial complex we chose before. I add the simplices by one, and for each of them, I verify whether it is positive or negative. All the vertices are positive, as we have seen, because their boundary is 0. So at the beginning of the algorithm, we increase beta 0 by 1 at each vertex. Then I add the edges. We have seen that the first 3 edges are negative. So I decrease beta 0 by 1 each time. Okay. And the fourth edge is positive. So I increase beta 1, the first Betti number. Then I add this diagonal edge. You can show that it is positive. You increased again beta 1. And then I add the triangle. You can see that it is negative. And so you decrease beta 1. All right. And at the end, you get the homology of your simplicial complex. Beta 0 is equal to 1, and beta 1 is equal to 1. Okay. So this is the algorithm. You may wonder, well, in practice, how can I verify if a simplex is positive or negative? We will see that in the last part of the lesson. So, oh, excuse me. Podemos falar depois?
É Cássia, eu não vou ficar muito tempo, tem menos hora.
Uma hora.
Não sei se eu vou ter.
Just quickly. Sorry. Okay. This is the algorithm. Now I want to show you some applications of it. I have 3 things I'd like to show you. The first one is something I told you yesterday. The 0th Betti number of topological space, the dimension of the 0th homology group, is equal to the number of connected components of my simplicial complex. First, Lucas asks, the output is just the Betti number, or can you deduce more information about the homologic groups? I would like to say that there is no more information from homology groups, but their dimension. A homology group is a vector space over Z over 2Z, and the only thing that describes a vector space is its dimension. So if you know the Betti numbers, you will know everything about homology. And I should say that in this course, we study homology in the field Z over 2Z. If you were to consider more general theory of homology, you will obtain other structures where the dimension is not the only thing you can obtain as an information. But here, this is the only thing we can obtain. Yeah. It's the only important part. It's actually the only part. So I want to show you here that the 0th Betti number is the number of connected components. But what is the number of connected components of a simplicial complex? The number of connected components of a simplicial complex is defined as the number of connected components of the topological realization of your simplicial complex. Unfortunately, we have another way of seeing it, because simplicial complexes are very nice to deal with combinatorially. I will define a combinatorial connected simplicial complex here. I say that a simplicial complex is combinatorially connected if for every vertices V and W, you can find a sequence of edges that connects V and W. Okay. For instance, K here, you can find a sequence of edges that connect this vertex and this vertex by taking this edge, but you cannot find a sequence of edges that connect this vertex and this vertex. So K here is not combinatorially connected. But what you can do, just as for connected components, you can find simplicial subcomplexes that are combinatorially connected. And you could call that combinatorial connected component, if you want. Okay. And what I say here is that if I can find M simplicial subcomplexes that are disjoint, non-empty, and connected combinatorially, and such that they cover my whole simplicial complex, then my simplicial complex as a topological space has dimension M, has M connected components, sorry. So you can study the number of connected components of a simplicial complex via combinatorial connected components. Okay, now we have that. I can prove the proposition. And we will need a very useful tool in graph theory that is called spanning trees. And actually, in this case, spanning forests. So if I have a graph, a simplicial complex, consider its graph, a spanning tree is a subgraph such that it contains all the vertices, such that it is connected, and such that it contains no cycle, it contains no loops. Okay, this is a tree. For instance, here you have a spanning tree of the first component of K. Here you have a spanning tree of the second component of K. And the spanning forest is the union of these two spanning trees. Okay. Now I will apply the incremental algorithm. I choose any order on the vertices. I will add first the edges of the spanning trees, and then I will add the other simplices. So first, we add to the simplicial complex all the vertices. And as we have seen, all the vertices increase beta 0, the first Betti number, by 1. Okay. Then I add all the edges of my spanning trees. And the property that they are trees implies that all its edges are negative simplices. Okay. The spanning tree has no homology. It has no cycles. So each time I add an edge, I decrease beta 0 by 1. And how many edges do we have? You can prove that for a spanning tree, its number of edges is k minus 1, where k is the number of vertices of the tree. Okay, so I add all the edges, and I decrease each time at the end of the tree beta 0 by k minus 1. So at the end, my beta 0 is the number of connected, the number of trees, that is the number of connected components of my simplicial complex. Then we have to add the other edges and the other simplices. And you can show that all the edges that are not in the spanning trees are positive. This is because a spanning tree is in some sense maximal. And if you add an edge, then you create a cycle. So when I add all the edges, I will increase beta 1, but beta 0 remains the same. And then I add higher dimensional simplices. They do not change beta 0. So yeah, this is it. My beta 0 at the end of the algorithm is the number of connected components. Okay. So as you can see, this is a proof that relies on really the algorithm of the incremental algorithm. And you can prove a lot of things by doing so. Keep that in mind. The number of connected components is an information that you can read on the Betti numbers. Okay. There is something else I want to show you. Thanks to the algorithm, we can compute the homology of the spheres. And this is very important. First, I have to triangulate the sphere. I give you here the optimal way of triangulating the sphere. I will triangulate the sphere of dimension n-1, the sphere in Rn. And to do so, I will take n+1 vertices. Okay, I will build a simplicial complex whose vertex set has n+1 elements. and then I can consider the simplicial standard and simplex. This is a simplicial complex which is defined as its simplices are all the subsets of B. Okay. So for instance, delta 2, I have 3 vertices, and it has all the simplices you can define on it, all the edges and the triangle inside. Delta 3 has 4 vertices and contains all the simplices you can define on it. It has 6 edges, 4 triangles, and 1 tetrahedron in the center. Okay. And now I will consider its boundary. Its boundary, delta n, is defined as the simplicial standard simplex, where you remove the maximal simplex, the simplex of dimension n. For instance, the boundary of delta 2 is an empty triangle. Okay. The boundary of delta 3 is this empty tetrahedron. And the result is that these simplicial complexes are triangulations of the spheres. This is a triangulation of the one sphere, the circle. This is a triangulation of the two sphere, the sphere in the space, and so on. Now remember that we defined homology groups of topological spaces as the homology groups of their triangulations. So what I have is that the homology group of the n sphere are the homology groups of these simplicial complexes. Okay. And thanks to
Professor,
yeah.
I didn't understand the second figure. It should be removed the vertices, right?
Can you say it again?
The second figure, the second triangle, we have a triangle and we removed its vertices.
No, you mean this one?
Yes.
You have two simplex inside the triangle, and you just remove the two simplex. You just remove the triangle, but you let the edges and the vertices.
Okay. Okay.
I can write something in this simplicial complex delta 2. You have the simplex 0, 1, 2, and you just remove it from this simplicial complex.
Okay, understand now.
Okay.
Thank you.
You're welcome. Okay, awesome. Now we have triangulations of the spheres, and so we can apply the algorithm to obtain the homology groups, the Betti numbers of the spheres. And it turns out that the Betti numbers of the n sphere are the following. They are 1 for I equal to 0 or I equal to n, and there are 0 else. Okay. So, for instance, I could deduce that beta 0 of the sphere of dimension 2 is 1. Beta 0. Oh, it's not drawn. Okay. I will write in the chat. Beta 0 of the sphere of dimension 2 is 1. beta 1 of the sphere of dimension 2 is 0, and beta 2 is 1. Okay. I will do the same with the sphere of dimension 3. Is beta 0 is 1, beta 1 is 0, beta 2 is 0, and beta 3 is 1. Of course, you recover the homology of the circle, as we've seen the other days. Beta 0 of the circle, S1 is 1, and beta 1 is 1, 2. Okay. So we will prove that. This is actually very simple. First, we will compute the homology, not of the triangulation of the sphere, but of these standard simplicial complexes. Up. These simplicial complexes, delta, they are homotopy equivalent to a point. I hope you can see that. They are balls, closed balls, and we know that closed balls are homotopy equivalent to a point. So if they are homotopy equivalent to a point, they have the same homology groups and the same Betti numbers as the point. And the point has very simple Betti numbers. Oh, a mistake here. The Betti numbers are beta 0 is 1, and the other ones are 0. I hope you can read the correction here. Okay, fine. And this is not Sn here. This is delta n. Okay. Now, what we will do, we will use the incremental algorithm for computing the homology of delta n. So what we know is that at the end of the algorithm, we will obtain the Betti numbers 1 and 0, 0, 0, 0, 0. So you choose any ordering of the simplices that satisfies the ordering I show you at the beginning. In this ordering, the maximal dimensional simplex arrives at the end. This is the last simplex of the ordering. Okay, but now, what if we run the algorithm without adding the last simplex? So for instance, with delta 2, it means that we run the algorithm, but without adding the triangle, the field triangle. We would obtain the homology of the sphere, because we will obtain the homology of the boundary of my standard simplex. And as we've seen, it's a triangulation of the sphere. But this last simplex of maximal dimension, it is negative. This is obvious because this is the only simplex of dimension n. So it cannot be included in a n chain, in an n cycle. So it has to be negative. And it means that if we run the algorithm without the last simplex, we would obtain this relation between the Betti numbers. You can say that the Betti number of the boundary is the Betti number of the simplex, the standard simplex plus 1, and the other Betti numbers does not change. And so this is how we obtain the result. Okay. Since we know now the homology of spheres, this is a very good opportunity to show a result that I showed you before, the invariance of domain. First, a question of Lucas. Is it trivial to prove that the boundary of delta n is homomorphic to Sn? This is not very difficult, but you have to be careful when proving that. The best way to prove that these boundaries of standard simplices are homomorphic to the spheres is by, well, you have to find a homomorphism between these boundaries and the spheres. A nice idea, I hope that you can see my drawing, will be to draw a circle here, and to define the homomorphism, you project up each point of the triangle on the circle. And you want to show that this projection is well defined and that it is a bijection and continuous. Okay, you are here in the plane, but you can also do it for this. You put it in a sphere and you consider the projection of each point of the sphere. Tiago asks, does this formula x divided by its norm work as a homomorphism? Yeah, exactly. This map you defined is a projection on the sphere, and you can show that this is a homomorphism. What you have to take care of is how do you draw your triangle in the plane? How do you draw your tetrahedron in the space? There are interesting choices for these vertices here. But this is a very nice exercise for you to do. So this is not very difficult, but be careful. Yeah, that's it. You restrict the map to delta n, the boundary. Okay. So now we can prove invariance of domain, which is really great. It's a very important result in mathematics. It says that if you take two different integers, m and n, then your Euclidean spaces Rn and Rm are not homomorphic. And so we can define the dimension. We can prove that. This is very nice. So we will do by contradiction. You have to do it by contradiction. Suppose that they are homomorphic and call the homomorphism F. F is a homomorphism between Rn and Rm. As you've seen many times, a good strategy here is to remove a point of Rn. I remove the origin of Rn, and by restriction, F becomes a homomorphism between Rn without the origin and Rm without the image of the origin. Okay. And now we will do something a bit strange. We will use the weaker statement that they are homotopic equivalent. as we've seen before, if two spaces are homomorphic, then they are homotopic equivalent. Okay. So we deduce that Rn without the origin and Rm without the image of the origin are homotopic equivalent. But now, this is something that we've seen before. Rn minus the origin is homotopy equivalent to its sphere, to its unit sphere of dimension n-1. And Rm without the origin, the image, Rm minus any point actually, is homotopy equivalent to its sphere. And you can see that easily if you look at the space, you remove a point. Around the point, you have the sphere. And basically, you retract all your Euclidean space on the sphere. Okay? You can define simple retraction to show that they have homotopy equivalent. And now, this is a contradiction. If these spheres are homotopy equivalent, then they must have the same Betti numbers, right? But as we've seen here, the spheres of different dimensions do not have the same Betti numbers. Okay, the Betti numbers of the sphere is 1, 0, 0, 0, 0, 1. And the last one is at dimension n. So if you take two n difference, you have different Betti numbers. And this is a contradiction. All right, this is it. Last thing I want to present you as a consequence of homology and its algorithm is something about the Euler characteristic. Remind that we've defined last week the Euler characteristic of a simplicial complex like so. You take the alternate sum of the number of its simplices of each dimension. Okay. We've seen that the circle, what is its Euler characteristic? 0. The sphere has Euler characteristic 2. The 3 sphere has Euler characteristic 0, for instance. And the proposition here is that you can compute the Euler characteristic of a simplicial complex or a topological space via this formula. You take simply the alternate sum of its Betti numbers. There is no number of simplices here. You just take the alternate sum of the Betti numbers and you obtain something which is its Euler characteristic. So one can say the Euler characteristic is an information already included in the Betti numbers of your space. We will do so by using the incremental algorithm. Take a triangular space, triangular space, for which you can find a triangulation, a simplicial complex K. You pick an ordering of your simplicial complex, as we've seen at the beginning. We will show that by induction, for every m, the alternate sum of Betti numbers is equal to the alternate sum of simplices, of number of simplices. So by induction, we start with m equals to 0, I should say. We start with, there is a problem here. This is the sum until m, and the sum until n here. What changes is not the, we always do the sum over all Betti numbers and all simplices. The only thing that changes is m here. we just upgrade the simplicial complex. So for m equals to 1, this is obvious, because on one side we have one connected component, so beta 0 is 1, and the other side we have only one simplex of dimension 0. Okay. Now, by induction, we suppose that it is true for some m, and we want to prove that it's also true for m plus 1. So we add a simplex, sigma m plus 1. Either it is positive or either it is negative. In any case, the term on the right in the equation here is increased by -1 to the d, where d is the dimension of the simplex. Okay, we want to show that it is the same here. If the simplex is positive, then we've seen that the beta d is increased by 1. So here we add a -1 to the d. If it is negative, this is beta d minus 1, which is decreased by 1. And so we still have an augmentation of -1 to the d. So we prove that these sums are always equal, and they are in particular equal for m equals to n. And for m equals to n, this is our full simplicial complex. And so we proved the proposition. All right. And this is it for the applications. If you don't have questions, we will go to the last section. Okay. So here is the problem we have. In my algorithm, incremental algorithm, I have to know whether a simplex is positive or negative. And I will give you here a way to compute that. Take a simplicial complex, order its simplices, and now we'll define a matrix, a very important matrix that is called the boundary matrix. The boundary matrix of my simplicial complex is defined as follows. You put every simplex in column, okay, sigma 1 to sigma 10, and in each column, you write the boundary of your simplex. So this is written here. In my column, I write 1 if the corresponding simplex is a face of it of codimension 1. Okay? For instance, sigma 5, this is this edge. It has as a boundary sigma 1 plus sigma 2. So I write 2 1s here in front of sigma 1 and sigma 2. Sigma 10, this is a triangle. We know that its boundary is the sum of its edges, sigma 5, sigma 9, sigma 8. So I put a 1 in front of sigma 5, of sigma 8, and sigma 9. Okay? The boundary matrix totally describe a simplicial complex. If you're given a simplicial complex, you know, if you're given a boundary matrix, you know what is its corresponding simplicial complex. Okay. And since we have a matrix, we can do linear algebra. We can manipulate the columns. And this is what we will do. First, remark that by adding columns one to the other, we can try to reduce columns to 0. And if we are able to reduce columns to 0, this means that we created a cycle. So for instance, here, I add sigma this column, sigma 8, with all the preceding columns, all the simplices of dimension 1 that appears before. This is 0, because I have 2 1s here, 2 1s, 2 1s, and 2 1s. 2 1s being 0. So the boundary of this sum is 0, and this is a cycle. So this way, we can try to find cycles, and this is exactly what we will do. We will reduce the matrix in order to obtain as many zeros as possible, and at the end, we will be able to understand the cycles of our simplicial complex. The process of reducing columns to 0, something you may know already, is called Gauss reduction. And in order to define the algorithm, I will use this function, delta, small delta. For any j in 1n, I define delta of j as the maximal index such that the ith entry of the column is not 0. Okay? For example, if I take j equals to 5, delta 5 is 2. Delta 5 is 2. Also, delta 10, this is 9. Okay. If the column is 0, if I have only zeros, then this quantity delta is not well defined, it's not defined, and I will say that delta is undefined. Okay. Now, I say that the boundary matrix is reduced if delta, the map, is injective, where it is defined. In other words, it is reduced if the last ones of every columns are in different positions. Okay? And if we are able to reduce such a boundary matrix, we will know all the cycles. And there is a very simple algorithm to compute the reduction of a matrix. I wrote it here, so let's read it. You start with a boundary matrix, and you want the reduced matrix. Okay? You have a loop for each column, call the index j. Then you look at all the indexes lower than j, I call I, and you check whether delta of I is equal to delta of j. Okay? And if they are equal, you add the column I to the column j. For instance, first step of the algorithm in this boundary matrix, you look at all the j's up to 8. Remark that for all these columns, they do not satisfy this condition. Okay? For instance, sigma 5, its delta is 2, and you cannot find a column before that has the same delta. Okay? Delta 6 is 3, and all the previous delta are different. Same for 7, but for 8, delta 8 is 4, and delta 7 also is 4. So you enter this loop, and you add the column 7 to the column 8. So you end up with this matrix. Okay. 1 plus 0, 1. 0 plus 0, 0. 0 plus 1, 1. And 1 plus 1, 0. Okay, let's continue. This column here, the 8th column, still has a delta that is equal to the delta of a previous column. Here, the 6th column. So you add this column to the 8th column, and you end up with this. And we continue. The delta corresponds to this one, so we add sigma 5 again here. And now remark that the column is 0. 1 plus 1, 0, and 1 plus 1, 0. So we found a cycle. This column now, its delta is not defined, is undefined. So we will stop with this column and go to the next one. And the next one, if we run the algorithm, you will add the 7th column and the 6th column. And you end up with this, where this matrix is reduced. You can see that the delta are all in different positions. Here, 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 and here. Okay. And now, something very nice happened. You can read from this matrix which simplices are positive and which simplices are negative. And to see that, take any simplex here. If your simplex has 0 column, then it is positive. If your simplex has non-zero column, then it is negative. Okay, so here I can deduce that sigma 1 up to sigma 4, sigma 8 and sigma 9 are all positive. And the other ones are negative. And that's it. Now we know easily which simplices are negative and positive. And we can use the incremental algorithm. Lucas asks, the columns that are left with a 1 generate the algebra of all the boundaries. If you are left with a 1, yeah, is this true? I think this is true. I think that the negative simplices, their boundary, you consider the boundary of the negative simplices, this will be a basis of the boundaries. I think so, yeah. Okay, conclusion. We obtained an algorithm for computing homology of a simplicial complex. You're welcome. Start by ordering your simplicial complex. Then, before using this algorithm, run this one. You reduce the boundary matrix. Then you know which simplices are positive, which simplices are negative. And so you can apply the incremental algorithm. And at the end, you obtain the homology of your simplicial complex. A small observation. Here, we are very close to persistent homology. The actual algorithm for computing persistent homology, the standard algorithm, is really looks like that. You will see it next week. And most of the current algorithms for computing persistent homology are basically trying to improve this part here, reducing the boundary matrix. And so, because as it is, it has its complexity is n to the 3, where n is a number of simplices, n cube. It's a cubic algorithm, so this is very slow. And yeah, people try to improve that. You can do better than n square to the 3. Yeah, usually this matrix is so sparse that even representing it as a matrix is a bad idea in general. You can do many more intelligent things. Okay, this is the end. So we've seen today the standard algorithm for homology. That will be soon persistent homology. It works incrementally, and it needs to test the predicate of positivity of a simplex. And we can do that simply by Gauss reduction. And also, I show you how, thanks to the algorithm, we can deduce interesting topological properties of our objects. And please have a look at exercise 31 and 34 for tomorrow. Thank you very much.